All right. So let me share.
Okay, yeah. As you're sharing, thank you for joining us today, Matthias and Shriram. We're going to learn about how to design programs and have a lively discussion afterwards. So whenever you're ready, please take it away. Thanks for your time.
So you should see, I don't know what you see actually. So I see that you see just the title slide. Is that correct?
We
No,
see
we see it's one E as well. We see two slides.
Oh, how did that happen? So let me stop sharing again. Where's my cursor? Damn it.
You're probably sharing the wrong view or something. Yeah, now we can see, yeah.
Probably. So okay, let's try sharing again. Come on. It won't let me. Oh, now. Maybe. Who knows?
Now we see your slide. We see Keynote without the screen sharing. We see like some code or something on the right as well. It's like some Emacs window. Ah, there we go. Stay with that. Don't do anything.
Good. I have to push some buttons. Okay. Thank you.
Good.
All right. So
well done. We're impressed.
You're impressed? Oh, that's good, man. So the title I stole straight off Jacob's email. He asked me whether I would be able to spend an hour with you guys to talk about the process, challenges, struggles, choice of creating how to design programs. I rearranged the words. Maybe I dropped one, but that's about it, right? So that's what you get today. And the only reason I agreed to do that because how to design programs is my love. So that's what I love to work on. Okay. So 1E, that means first edition. That's about, I would say, the idea that I would write a book along those lines, roughly, came to me about 91. And at the time, I was a lucky bastard. I did research on a whole bunch of stuff that got me promoted to full professor within 4 years. And then my chair pulled the trick on me. I said, now that you're a full professor, wouldn't you like to teach Fundamentals 1 or CS1 or whatever you call it, the first course? And I thought about it before he asked, and I said, absolutely. That was a mistake because my life changed forever. So that was my research program, and I continued this for a while. Good results, whatever. But I started teaching Fundamentals 1, CS1. And after teaching it once and watching somebody else teach a very similar course, his name is Bob Hopper, I asked myself, why am I teaching that? Why am I teaching? What am I teaching these students? I taught it again. So I went back to Rice, taught again. And I said, oh, I know why I'm teaching this. I'm a semanticist, and semantics is about understanding programs and validating them and knowing that when you click the run button, they don't launch a nuke, but they actually do something good for you, right? So I wrote 700 pages of stuff about this, and 700 polished pages, actually. I went back and then I did this. I threw them away. Because a whole bunch of stuff had happened. I had actually figured out by random things that this was completely the wrong approach of dealing with CS1. There's a whole bunch of stories that went into that, and it would take too long to tell you all the stories, but there are 3 founding stories that actually happened. One of them is a grad student asking the right question at the right time. Another one is a babysitter not being able to answer a question at the right time. And the third one is a guy called Bruce Duba saying, we should start teaching them with Booleans, like whatever that means, right? So 3 founding stories, and that triggered me to say, this is the wrong way to go. I shouldn't write a book that uses my work, my research to write to explain semantics to freshmen, for heaven's sake, or concepts around that. So I did something different. I set a different goal. And the goal this time was to bring across and understanding of programs, how they are constructed, why they are constructed in a certain way. And to align that with teaching people who are in high school still, or maybe middle school, algebra. Because this babysitter story was the idea that I was able to explain with my first revisions in the back of my mind how to break down a problem and solve it for that person, right? Or with that person, and then solve it for her. So I started teaching CS1 again. And with Sriram and Robbie and Matthew, I started teaching Teach Scheme. Actually, so there's a bang at the end. I will reveal this big secret that this is the only postfix position in our entire world. And it means not. We didn't teach scheme. Anyway, so we taught something different, namely how to make programs systematically, right? Step by step. And bring this to students who are like maybe ninth grader, right? And then I spent an inordinate amount of time observing, watching, listening. I would go out to high schools in Houston. Every week I picked a high school. There were 3 or 4 of them that we had trained at the time. One was in a Hispanic barrio, the other one was in a Vietnamese suburb, and the third one was a very, very elite school, probably the most expensive school. Of course, they only spoke French there, so never mind that part. But so I did that for a while. And that shaped more and more how I understood that we were not teaching scheme at all, for example, that we were not teaching program design correctly yet. I had to come up with additional steps, with additional ideas on how to do things right. So it's very important for me to waste a lot of time spending with teachers, sitting down with students in high schools, even having some students come to my house sometimes. And that eventually helped me to write a completely new book. I literally opened an Emacs buffer with a completely new thing and said, how to design programs. So that was the actual beginning of how to sell programs. And then what happened? Then you repeat that for 5 years, over and over again. And at the same time, by the way, do research, just so that NSF finances your PhD students. I did this over and over again. And it was a very difficult process, because when you have only many months a year or many weeks a year to write, just getting restarted after you've taught CS1, you have a head full of ideas. Now you can start again, but then you have to write a proposal. Then you have to look at a dissertation. Then you have to write papers to get them out. You forget again. You have to get all these invariants, all the logic of the writing back into your head. So this 5 years is 5 years, partly because you don't have time as an advisor or as a professor to just sit down and write a textbook if you want to change with that textbook how things are actually done. So that was 1E. And then after I published that, around 2001, I think I handed it over to MIT Press. I was very happy. It's over, book is done. I can write the next book. Well, that was not true. What I realized was, and I don't know how, I forgot how it came about. I was not actually teaching fund, I was CS1 at the time. But suddenly I face pumped like that. And I realized what I was teaching with how to design programs was how to design functions. But how do you glue functions back together into a program? And I had kind of, in the back of my mind, I was saying, our batch programs is what we write, COBOL programs where you read in, personnel files and work hours and you print checks. And it's straightforward. And you just write the functions. But I didn't write it down. And that was wrong. And I knew how to write batch programs. You see right here, you just write a 3-liner. Read from wherever input device you have, process that stuff, and then write out the result. That's a batch program, right? And what I taught students was this red thing. Process this input so that it becomes the output. So I taught only one small fragment of how to make programs. What I also realized, and essentially I think it was Sriram who kicked my butt about this, was programs are no longer batch programs. That was in 1975 when you were born. I was born before that, don't get me wrong. What we write now are interactive programs, reactive programs, right? And of course, we know how to do that, right? I had no clue. I mean, I had written GUI programs, desktop GUI programs with our framework, but that's not what you can teach students. It has nothing to do with the overall goals of how to design programs. Remember, how to design programs is about teaching systematically, building programs from scratch, relating it to the algebra that students learn in ninth grade and helping them figure it out too. So, whoops, I'm stuck. All right, can you guys hear me?
We can hear you. The slide's not changing.
Yeah, not for me either.
Turns out the slides are also not a reactive program.
Not reactive programs, yeah.
Fortunately, I didn't use my own code. I used Apple's Keynote, and I can't even, oh, there.
There we go. Yeah, we're good.
Oh, woo.
And now we have both the boxes, all three boxes visible.
That's something okay, there we go.
There you go. Good, good.
So I spent at least a year thinking about it, playing it back and forth. And what I wanted was to create a library that connects to algebra. So there is no imperative stuff visible in GUIs. Wow, think about this, no imperative stuff. That was not something that people even in Haskell really did at the time, or what they did was not what I wanted, because it was high order functions with streams and who knows what. I want to break down the GUI thing into its pieces. And I want to be able to, then the pieces meaning the functions are the fundamental building blocks. And then I want to be able to design these individual pieces and plug them just back in. That's how Big Bang came about. And Big Bang is a framework that I created in this time. The actual creation probably took like 4 weeks, but thinking how to get it right took forever, and a lot of detours. And what Big Bang does, it says there is a state, and the state needs to be visualized. So think of it as a virtual DOM, and there is a way of visualizing it, but I allow the students to write that function that says state goes to the visual element. I have things that must handle gestures from the input, like keyboard events, mouse events. If you run this on the phone, you should be able to have swipe events, left, right, up, down, whatever, who cares? And you want to also bring in events that have nothing to do with users per se, namely clock ticks and messages. And for each of them, you can write handlers, and then everything just works out. So I can write, with Big Bang and Universe, I can write distributed programs in CS1, and the students write at the start, the Hello World program is now, a word came in, let's display the word. So there's some dictionary server that throws out a word, and your job is to put that word on the screen. 3 lines of code. Okay, so those are the programs. And now I can say I can give students a systematic design of programs, how functions come about with their signatures. I didn't write that down now. And then I can focus on bringing back what how to design programs did before, namely teaching these functions and designing these functions systematically, and still staying creatively in the algebra world, and have 9th graders or even middle school students do that. At the time, we had a program that's called Compass. It evolved into Bootstrap, which is what Sriram is running now. And I wanted to be able to help my undergraduate students at Northeastern to run this Compass program, and eventually with Emmanuel Schanzer, for the high school students middle school students in Dorchester. And that's a challenge, I can tell you that. But getting them to say, I wrote a video game in algebra, wow, things got started. So that was the thing that I did. Now, of course, I realized, I can throw away how to design programs, because it wasn't right. I had to go through the whole book and remotivate and redo everything so it fit into the framework of Program design means function designs, means either batch programs or GUI programs. And they must dictate how the building blocks come about. I went back to my cycle. This time I didn't spend a lot of time observing what students can do and cannot do, how students understand stepping. I did some of that at Northeastern because I started once again teaching CS1, but it was less of a factor in redoing this book. You literally go through your book and you cut out pages. I cut out 500 pages and wrote them from scratch to get the second edition going. And it was again the cyclic process where you have to go through a whole bunch of steps. Now, my steps changed. I had to find examples. And the examples, I realized, had to be actual programs that evolve over the course of the semester. Why? I'll get back to that. So the projects have to be big, interesting, motivated. For example, students walk in and say, this semester, we will write a text messaging system. This semester, we will write a little Spotify. Those are the kind of things I did then at Northeastern, right? But how do you break that down so students get started in week 1, homework 1 or end of week 1, and then end up with something that looks like what they know from their desktops or from their laptops or from their phones, right? So that's the really difficult, challenging part here, how to do that right. Okay, and then you rewrite lots of sections in the book, and again, in the same time, you play researcher and advisor, and you raise lots of money and blah blah blah, whatever, just to pretend that you're actually doing research, because nobody thinks this red looking thingy is research. They just think that's teaching. But real teaching at a university is a scholarly activity that requires lots of research. So in particular, you want to write new homeworks every single time you teach this course. And when students ask you, can I publish your solutions online on my GitHub? I say, yes, please do. Because I write a new solution and a new problem set every single semester. And the problems that I reuse from semester to semester are not graded. So that's where the effort goes, right? So what are the actual goals? So this is a big picture painting thingy here today. This is not details. So I believe that programming has to be taught as a socially responsible activity from day one. That's where how design programs comes from. What does socially responsible mean? Well, obviously, very few developers have anything to do with the end user. A marketing department, a project manager, somebody discovers something that wants to be done, add a feature to this thing, make it throw nuclear bombs or whatever, a new feature. And then you as a developer, the only choice you have is to say, yes, I will do that. I don't like nuclear bombs. I don't like to play those things. I walk away from the job. Most of the binary choices. So where does social responsibility kick in? It kicks in as you as a programmer are sending a message to the future, maybe 6 days from now, maybe 6 weeks from now, maybe 12 weeks from now for a freshman, or maybe 6 years or 60 years. And you are responsible that this message arrives in a way that that person who picks it up, an older version of you, or somebody who was born after you died, that person should be able to pick up your code and understand it in a reasonable amount of time and change it. Fix bugs, make it faster, add features, you name it. Systematic design is what helps these people. It helps because for students, it breaks problems down explicitly, not implicitly. In all other textbooks, you will find implicit breakdowns of problems. Copy my behavior, try to find the breakdown. And we pretend we teach how to break down problems. We don't, not in CS1, we do. Our textbook does, right? So they understand the problem, hopefully. And then when you actually create it with this pattern of how did it grow? How did this thing grow systematically? When you look at it again, these things kick back in. If both the sender and the recipient understand that system, either by being taught or have acquired as a professional, they know what's going on. Okay. And all of that has to be matched with programming assignments that intrigue students, that work well, and that grow. So that's roughly what went into how to design programs 2E when I finally understood what I was really writing. So 3 books, probably 3,000 pages of text. When you buy it, all you get is 600, but you don't want to read the other 2,400. Okay, that's a process and what the process was aiming for. One last slide. Yes, but challenges, struggles, and joys. Well, in my mind, the design that I teach, the system I design that I teach how to set in programs, sets up a convex hull of designable and not designable programs. And that convex hull is grown in 6 major steps, roughly. So every example I come up with has to fit into this convex hull. Every problem every big project is broken down has to be broken down in the convex hull that matches a particular chapter or week in the book or in the calendar, right? And so you have to grow through these layers of convex hulls. Now that gives rise to an incredible struggle. Your colleagues will not understand. Your colleagues will not understand what's going on because this is a completely different approach to teaching CS1 than what you find at a podunk university, like Northeastern. We actually teach it, right? But as some of you know, we have acquired a bunch of colleges and their instructors aren't even able to solve the problems. So we fly out people from our staff to teach them how to solve the problems, which our students have solved in the meantime, right? That's how bad it is when you struggle to get colleagues on board. I'm not saying that happens everywhere, but this is an example from my own house. I don't want to blame any other universities. I'm just blaming our university for growing in a way that is not appropriate. That's struggles. Choice. Just in case you ever think you're writing a book for anybody else, it's not true. Unless you write fiction, or maybe an autobiography for your grandchildren, you're not writing a book for anybody else. You're writing a book for your own joy, for writing here. When I am able to rewrite a program the 10th time, the 13th time I wrote here, and it finally fits in the convex hull that I want to teach right now, and I know how to explain why that is a systematic place to get to that version of the program, I'm unbelievably happy, right? And the same thing is true with writing, right? I have rewritten sentences, paragraphs, pages, I don't know how many times, until I know that the steps are the best I can come up with, at least at that point in time. As you saw, I threw out an entire book. Actually, I threw out 2 books. One is unpublished to get to that point, right? On occasion, you get an email from you get emails from students. Don't get me wrong. Ignore those. I mean, you can read them, whatever. But the emails you get on occasion are from developers, people who have. Sometimes I go like, I have programmed my entire life. I'm now retired. I picked up your book as a hobby, and it changed my mind about programming. That's an unbelievable email, and I get one of those maybe 5-10 times a year. That's really cool. And it's been going on for years now. Sure, I'm getting some of those too from the authors list, right? And then everybody says, and I can't believe it's free. So not, so why not? That's what we did. Because it's not for the royalties, it's for the joy of creating that book. And that brings me to my last slide. I want to say thank you very much for coming. This is the end. I have to thank my co-authors here, Matthias, who's not here. Of course, Robbie's also not here. But Shriram is, and he continued where I left off and projected and turned the vision that I had in my head into an amazing program that's now run. And I should not forget somebody who's not a co-author, namely Kathy Fissler, who has contributed tons of stuff over the last few years in the same manner. And the secret is, of course, Shriram and Kathy are married, but don't tell anybody. That's what I have. Thank you very much for listening.
Thank you so much. That was a wonderful presentation. I'm going to start us off with some questions, but everyone else, please feel free to jump in at any time when it makes sense. But the one that I've been puzzling over for a while, Matthias, is that there are many people who have many different opinions about programming, and they seem to have these different cultures or tribes. Like the Haskell people and programming language theory people will be like, oh, dependent types are so important. You write your type signature and the rest of the program falls into place. It's so easy to modify your code without needing to rerun everything. And then the Clojure people will say, oh, this is built on Java. It can be everywhere. And it's such a good design and you can do so many different things, and the type system actually gets in your way and introduces coupling. And then you have the Python people who think they can glue everything together and it's wonderful. And the JavaScript people who like building visualizations and web apps and things. And to me, I think there is a sense in which design is critically important, but how is it that we can even say there is a way to design programs?
Okay.
Like, sort of questioning the premise, if that makes sense.
So I hear two questions, and I completely disagree with you that there are many ways or many opinions of how to teach programming to CS1. I think there are two. Okay. And I will describe the one that has been around for 60 years. And I happen to know that because I sit next to people who teach that way. Right? So the first group in my mind takes a currently favorable and fashionable programming language. It could be Haskell, it could be Clojure, it could be Java, it could be programming, you name it. Just something that's favorable and fashionable, ideally favorable, because the teacher has to like it, that's the real thing. I like that language more than anybody else, so you better follow me, right? Kind of thing. If it's fashionable, even better, because then you can tell the dean, I bought IBM. Sorry, these days it doesn't make any sense anymore. Way back, you used to say, he bought IBM, he can't be fired for that. Look it up. It's a really cool saying, okay?
You don't know what IBM is, Matthias.
IBM is a snack thingy in Maine where you buy lobster rolls. Just kidding. You know what IBM is? It's a software company now. Back then it was a hardware company. So whatever. Sriram wants to say something and he can't. He's muted or something.
It's called services. They call it services. Sorry, I'm just
excuse my language.
Don't mind me. Keep going. Ignore me.
So that's why I said you don't understand what it is. Google the phrase. Okay. So you pick this language and then you teach the way you were taught. Well, how were you taught? You print hello world. And then you introduce variables. And then you may introduce an array or a list, and you iterate over that list with some kind of looping construct. And then you know what I'm getting, right? And if you are in a class-based language, you may end up with classes maybe at the end of CS1. And if you're in an object language like JavaScript, maybe you see actual prototype thingies. Who knows? I doubt it very much. So, you teach the same way. And how do students learn? How are teachers actually teaching what students should program? Well, we solve a problem in week N with the features, the syntactic features available at that point in time. That could even be in a concurrent programming language, right? So we teach this program, and then we give assignments, homework problems that look more or less like that. Like that meaning, you did sorting on numbers. Now let's do sorting on floats. Now let's do sorting on integers, or sorting on personnel records where an integer is buried down there, right? And then students kind of start with, hey, let's copy this code over there. Let's modify it a little bit. And we bang on this on the lines of code until running it from the command line and interacting with the program maybe works just fine. That's how CS1 is taught by everybody who has picked, as you said, Haskell, Clojure, Java, JavaScript, Python, whatever. By the way, then in my mind, they rarely get as far as the second group, which is people like the 4 people are listed here on this last slide. What we teach is very different. We ask the following question. If I give students middle school algebra as a programming language, they have functions, arithmetic expressions, and maybe conditional, because stepwise functions in algebra 1 or pre-calc. So somewhere around there, 8th, 9th grade. what can they do with that? Right? How do we teach how to build a function, right? And what can we do with that for programs? If you look at the math instructions, the algebra and pre-calc thingies that you see there, what you see are word problems. And students are terrified of word problems. Well, so math books here have a certain way of teaching that. Well, what we do is we teach students, here's a word problem. Here are 6 steps of how to break it down into things that an instructor and you can eventually come up with a cool function that does something interesting visually or sound-wise or whatever, right? And then you say, oh, how do you arrange that? What kind of data have we had so far? Well, we had numbers. Numbers are boring. Let's throw in pictures as atomic values, like numbers, boring. Let's throw in strings, atomic values. Maybe you can do substring or that's about it. Fine, boring. So you have finite data. So in the other direction, in the direction where you grow now, you go like, what if I want more interesting, what if my program wants to deal with more interesting data in the real world, like mouse clicks, right? Or maybe like a list of friends that I want to invite, or maybe my family tree, or maybe the T-graph that I want to navigate or something like that, or the graph on Twitter where I want to chase down things, right? And so you grow the data complexity in the other direction. And when you grow the data complexity, you look whether the language, this very small language you have so far, can actually get you there. That's the convex hull. And only when you've exhausted the convex hull, you go like, well, let's add a syntactic feature, like, conditionals, or let's add a syntactic feature like a loop. We don't use loops actually, but whatever. Think of them as loops, right? So you keep going through that, and so you grow your language, which is why we have my co-authors develop languages, a framework for I make the languages, but a framework for making languages. So students grow through the languages, but only when the data and the design challenge requires to make the language bigger. So it's a completely different approach to teaching, Jacob. So there's one group, and they may look different to you, and they're not, right? So that's the first question you asked. Now, if you want to go about and say, well, teaching developers who are already working on stuff, that's a different question. I'm talking about CS1. Okay? And while I was answering your first question, which you didn't even ask, I forgot the second question. The actual question you asked.
No, that's okay. That's a great answer. The second question, and I have one more after that, and then other people can start thinking about theirs and jump in. The second question is, or I'll modify it a bit from what you just shared, which I do appreciate the significance of the 2 different camps of the convex hull framing. And perhaps this is helpful for the second question, because if you are looking at growing out this language convex hull to a place where you can do all the programming you want, maybe for theoretical reasons, it's a Turing machine level computer, and maybe it's something else.
Hold on, Jacob. Turing, okay. You get everything you want from the beginning. You could write a Turing machine in the first language. That's the wrong.
Sure. I'm talking about the most developed language.
No, that's the first language. You can already write Turing machines.
Yes. Okay. So sorry. Let me just. The question is, different languages start with different primitives, right? Like a Haskell person has a different opinion about programming than someone using Scheme or some flavor of Lisp. And I'm curious. I was asking about sorry, I'm just trying to phrase it properly. Why is there a way to design programs?
Yes, absolutely. So that's a fantastic question. I forgot I should have written it down. Just one more remark about the languages stuff. I choose, and I now insist on teaching an untyped language in the beginning. But the language, the design, if you listen carefully, I said I grow the complexity of data. That is, of course, a type-driven approach. So the difficulty, of course, even there is, how do you do the first step in writing down the type? Which, of course, you should, if you ever have a dependently typed or Haskell typed person in this room, you should challenge those people like Stephanie. I've challenged her many, many times. She's my former student, so I can do that. How do you actually design the types? How do you design the complex types so that everything just falls out? Okay. So is there a way to design a program? If I make the convex hull small enough, which I do initially, very, very small, for reasons that have programming language technical things, there's another talk, right? I make it very small so that students comprehend this whole language in one lecture and really comprehend its meaning, right? We have a machine that tells them how to calculate out the meaning of the program. It's called Algebra 1 from middle school, right? So in that world, there is usually one way of designing a program, okay? So let's throw in something interesting. How do you make lists? You need a self-referential data definition, a recursive type, right? And to make recursive type systematically turn into code, so the code mirrors the type, which is even, it's just a comment, right? You write down a recursive function, but it's a recursive function that mirrors exactly the recursive type. So wherever there's a self-reference in the type definition, there's a self-reference in the processing system. If there isn't one in the type, then there is none in the code. So the code mirrors, in a sense of what mathematicians call isomorphism, the process template. And then from the process template, you go down to the function as a homomorphism. That's the, so since you guys are a bit mathematically inclined, I can use actually big words, right? That's the idea, right? So you can do that. And now when you say, can I write a sorted list of functions with the process of writing down an isomorphic thingy as a process template, and as a homomorphic thingy, you get one sort algorithm, insertion sort. Well, you grow the students a bit more, you grow the programs a bit more. And you get to the point where you go like, what if I allow you to not just apply recursion to where the data definition is, the type definition is self-referential, but where you say the data represents a problem, and I can somehow mangle the data to come up with a problem in the same class, but it's not chasing down the self-reference in the type. Ah, that's recursion too, but it's divide and conquer recursion. You teach that, and you show them, oh, merge sort, quick sort. And then you have now, when you say sort, you have 3 different ways of writing it down. And that's where you're allowed to write down a comment. I'm using divide and conquer algorithm, blah, 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 right? So you don't have one way of designing an algorithm, a what specification. You come up with many ways. That's for programs that come up, the function parts, the building blocks that come up over the semester, right? One level up, you have another choice to make. That's why I really think Kathy has done an amazing yeoman's work. So Kathy Fissler, that's the reference on the last page here. When you have a bigger problem, one thing we teach, and I don't teach particularly well yet, is you need to have a function that has many tasks to perform. We tell students you must break down this thing into a composite function, composition, a la Algebra 1, and atomic functions that perform an actual step of work. Often, in the problems that we see at that level of programming, the intermediate data is clear. Now, let's step out of this framework of CS1 for a moment. Even in CS1 it happens, but it happens more equally, more common in the UNI program for real, right? You know that a function has to perform 2 different computations. You know it deep down, right? You see that. The problem statement tells you. But to break up F into G and H, you need something in the middle that is the data you communicate. You communicate the result from G to H so that F is just G composed with H, with composition maybe for loops or map or whatever, you know, but just composing G and H. Coming up with the intermediate data is another choice point in design. And that's what we can teach students about week 3 or 4 already. Hey, I could choose this, or I could choose that. I went, my oldest son is a teacher. He trained, his degree is in history, but he's the only one who understood math. So I asked him to teach math, and now he's teaching math with programming, like I taught him. So I gave him a problem. How do you represent, this is actually a week 3 problem from our course, and I've taught it many times. Let's implement a program that is a text field editor, right? A text field editor. Now, all of you, simply use the GUI framework in the DOM or desktop GUI framework and say, give me one text field editor. You don't think about what, that's not what we're teaching them. We're not teaching them how to use a piece of software that exists. We're teaching them how to make it, but it's a cool example. You need to break that down into different functions that do different things. That data representation could be the prefix and the suffix, the reverse prefix and the suffix, because you really want the reverse. You want to be able to at the end, you want to bang at the end. The in between is a cursor, right? You could come up with a string and just a number that tells you where the cursor is. 3 different data designs. Now follow through and see how the functions you design compose around 3 different designs. As a matter of fact, in my courses, and I told my son to do the same, I let 3 different groups of students come up with these 3 solutions. We compare them and go like, oh, we have 3 times systematically designed from a different data definition, a program that visually implements the same behavior. Now we can actually discuss differences on how they differ as a message to the future developer. And clearly the one with the reverse and the suffix is the one you want to use. And of course, real editor have more interesting representation. That's an example of where you make choices, and the choices are leading you one way or the other. And those 2 things make programs not unique, except for the very first 2 weeks, right? And you can see, but the cool thing is you can now discuss design differences and design choices you make. ChatGPT will not be able to do that. But what the other group of CS1 teaches will be covered by ChatGPT in a year or 2 from now, or GPT, you know, Chat 55 or whatever it's called. All right, back to you.
Matthias, I have a question. I took a really wonderful Intro CS class in my freshman year with Jonathan Coates, and he did an amazing job, and it was in C, and it was really hard, but also very rewarding. And I loved it, and I learned a lot, and it really made me interested in programming. I actually left electrical engineering and became a math and computer science double major. However, more than 50% of the class dropped it because it was too hard. And I've seen over and over that like the most rewarding, most meaningful computer science classes are ones like your IPPL or Pete's, formal verification class, or this class I took with Jonathan Coates, where to a talented student who's going to work hard, they're rewarding and great. But to somebody who just kind of wants to learn programming but doesn't like really care that much, maybe they're a biology major or something. It's sort of the juice isn't worth the squeeze, right? And so I wonder, what do you think about how to teach people who are not computer scientists or not going to be a computer programmer professionally, but they will need to write some code?
I didn't pay Max to ask this question, but I'm very happy the question was asked. So let me divide this question into 2 pieces. I will drop the suffix that you said. They have to program a little bit. When I say I want to teach 9th graders or 8th graders and 10th graders, I look in the mirror and go like, why the hell would I want to abuse little children and teach them to program? It's abuse. Okay. Why are we teaching them math? Well, in the United States, you don't actually teach math, but ignoring that. So I'm sorry, this is my arrogance as a foreigner coming here and seeing my children suffer through so-called math education in good schools. We're teaching them so that when they grow up and become professionals, they'll learn the right way to use the piano keys. Right? Because you can teach piano the wrong way and kids will hate it. You teach it the wrong way and they get carpal tunnel from just playing piano, but they can also enjoy piano, right? What's the essence of piano here? What's the essence of programming, right? If you teach systematic design, what you actually teach is systematic problem solving. You teach a mental attitude, and the attitude is, if you go slow, but step by step, you will get there. If you go fast, and you can't believe how many little boys, I'm calling them little boys, I'm sorry, in my Fundamentals 1 course, want to go and just do it. I want to get it done, right? I don't need that design stuff, that systematic stepping bullshit. The teacher doesn't know what he's doing, right? If you do that, you get there. And of course, these little boys fall over their feet like little toddlers when we get to week 5. And we show we can do mutually recursive traversal of file systems. And I go, huh? I need a stack for that. I said, why would you want a stack for that, right? And I need a queue for that. What is a queue? I don't know what a stack is. I don't know what a queue is. Just follow the design steps. I don't know what they are. Well, read the book, right? So when you do that, right, you're drilling down on people. And then if you also explain to them at the end that the design steps that they learned can be ported to geometry solve problems, to poetry classes, to photography things, to a surgeon's prep list for a checklist for getting ready for surgery, and you show it to them, eyes pop up. And I mentioned, except for the surgeon thingy, I mentioned examples where students wrote back to me, students I did not train, students that teachers taught that I trained at Rice. Students wrote to me because I knew I was behind the program and says, I just used the design recipe for my poetry class and I got the best grade. Thank you so much. Like, that's why. And that's why I can go to the bathroom in the morning and look at the mirror and say, like, I'm doing okay by those kids. Okay? And I don't want them to program when they graduate. I want them to have the mindset, problems can be solved step by step. Don't jump ahead. You will trip over your own feet and fall. Now, your last sentence tripped me up. There are people who want to program a little bit, right? That's why I mentioned the surgeon. So one of my friends in Houston was an anesthesiologist who did liver transplants. It's a 12-hour surgery at the time. He had more computers than the entire computer science department of Rice together. He programmed more and he read more in math, right? Because it turns out you really want sensors in the bloodstream that figure out where the drug is and how fast the drug goes. While in the first hour and a half and the last hour and a half, a person has to do that. Otherwise, things go haywire. In between the 9 hours, for heaven's sake, why shouldn't we have programs take over, right? To get from there to that point where he was able to do Stokes' law and turn it into Pascal code, whatever Pascal is, that took him from the beginning of this class reading up on a lot more stuff. He was completely self-trained. And that's what I'm hoping. I'll lay a foundation. And I'm hoping that when they pick up a Python book, they know it's bullshit. I learn enough from the syntax, and then I apply the slow stepping that I learned way back, and it goes better. My oldest son went through exactly that. He's like, he took a Python class from a college in Austin, Texas, whatever the college is. And he was devastated. We teach very interesting things, Python. And like, he asked about unit tests, for example, because unit test is one of those things we showed in the second week. And the teacher, that's such an advanced concept. You don't need to learn this in the CS1, right? So that's how exactly. So he decided to drop this crap and just pick up the book and squeeze. He was forced to teach Python in school. That's why I learned it, and squeeze Python from the book into the schema that he learned from me. That's my answer.
That's great. Does anyone else have questions they would like to ask? Otherwise, I can keep going for a few more minutes.
I guess I just wanted to share that you talked a lot about how like you're not really talking about teaching developers, but I'm a developer with like no academic background whatsoever. I mean, I took like a couple classes for community college, and I found your book super, super helpful in like clarifying my development process and like kind of slotting together all these different practices that I tried, you know, in various languages, like learn TDD. I learned about types and when I learned Haskell, and it's just kind of like put it all together. I'm like, oh, this is how I can figure out how to solve these problems without like just cramming algorithms, you know, the like the job interview books or whatever. So
funny,
super
funny
helpful.
I don't know your name, but funny you say that. Last week, so I was in Germany last week. The week before, just the day before I went to Germany, and now I'm back. I gave a talk at Google in Cambridge, our Cambridge, not the other one. And it was about socially responsible software development. That's what I call the next book I'm writing. So the background is that I'm actually scaled up this CS1 course into CS2, where we apply the same techniques, the same design techniques to Java. There's a version of the book that I never published on my webpage. Then we scale up one more time and say, now let's look at architectural design, where you have more patterns and architectures to make choices for intermediate breakdowns for you. And then I teach another course on top of that called software development. And I call it socially responsible software development. And in that course, I teach developers. I really mean developers. And and somebody asked before, well, what if, you know, hard courses, well, yeah, like IPPL or whatever. It's a hard course because I want students to understand you are responsible for the person who receives your message. And I'm going to teach you techniques like presenting code properly to your peers, listening to presentations and understanding how to critique and what to critique, organizing code so you can hand it over to the next pair or third through the semester, right? Stuff like that. Real techniques on how developers act in the real world or should act in the real world to make this message available to the receiver, properly available, right? Because we are turning thoughts into bytes and bits, and they go over there, and the programmer receives it, needs to reconstruct them. So CS1 is what you see as how to design programs is only the very first building block of that step. But it's separated from the other steps because CS1, as I mentioned in my previous answer to Jacob, is also intended as you don't ever program again, but you learn to organize your thoughts about problem solving. So that was, so I do teach developers, but not in this course. And there's a whole ladder of things that go up. Guys, I'm so sorry. I give you a short answer here, but I have 4 minutes left. I have another meeting coming up at 6 o'clock my time, East Coast. So one last question.
That's great. Does anybody have another question they would like to ask?
Matthias, what do you think of garbage languages like MATLAB and R? Can people write good code in horrible languages?
Yes.
Okay.
So I have written one paper on R, adding stuff to R. At Rice, we actually had somebody turn the design recipe into a non-CS course, a CS course for non-programmers using MATLAB. But it is a sad story how the developers of these languages don't actually know enough about languages to make a good language. That's a different story. You can use Python to write good programs. I would consider Python worse than the other two. It just so happens to be fashionable and has a lot of libraries that make people's life easy, but that's not the same as being a good language, right? I let students choose. So in the course, I mean, I forgot the name. I'm sorry, I didn't catch your name. I'm pointing at the previous questioner. In this course, where I mentioned the software developers, I actually let students choose whatever favorite language they have. Right now, I will prefix this. I will say this twice. On the average, right? On the average, the Python programmers do worst. I see everything in a language. I see Haskell. Actually, this semester, OCaml did much worse than anything I've ever seen before. But that's I studied the program, and it's the son of a faculty colleague who was mentioned before, so I don't want to mention anything more than that. It was a bad choice. But I've seen Haskell, I've seen OCaml, I've seen Scala, I've seen Elixir, and I've seen everything. I mean, not everything, a lot of languages. But Python on the average works. Now, what does on the average mean? That means last semester, one of the best code bases was written in Python by a woman with two partners. We changed partners, but she kept the code base for reasons that doesn't matter here. Who was just outstanding in actually using the design ideas we taught and applying them to the language, right? But the vast majority of Python programmers just didn't get it off the ground, right? So that's what I mean on the average means. Okay.
Okay.
Thank you so
We're
much,
at
Matthias.
time. Thank you. This was a wonderful presentation. We really appreciate your time.
All right. I hope we got something out of it. I have to run. Sorry, guys.
Bye, Matthias. Thank you.